all this stay-at-home stuff is giving me time to practice the harmonica. Looks like I better keep practicing. Anyway, just to, we're going to try this video. It looks like some of the problems with getting videos up into Google Docs or Google Drive has been solved. So we're going to see how this works. I've also identified a couple of Khan Academy videos that should work well with this. I'm just going to augment some of that to see if we can get a good introduction to solubility equilibrium, the last new concept that we need to cover before the AP test. The rest of this, after this week, is just pure review to get us ready to see what happens, see how they're going to do that test. So the solubility equilibrium, I'm just writing this one. You might have to pause the video to be able to copy some of this down. Solubility equilibrium, what is the molar solubility of calcium hydroxide at 25 degrees C? And then I'm given the equilibrium constant YKSP, and I'm going to explain that now, is this. So what we are going to do, and this again is section 17.4, page 737 in your textbook. So it's right there. I'm going to follow the textbook sort of closely, and then between your textbook and the Khan Academy videos and this video, hopefully it makes sense, and there'll be some practice to do as part of this assignment. These solubility values, where did I find this? You can actually, there's a table of them. It's Appendix D. Table D3. At the end of your textbook, it's page like 100 and page 1116 at near the back of your textbook. So let's do this. So that's where I looked that up. Now let me explain KSP. We've looked at this. We said KEQ equals KC. It's the same thing, right? If we're talking about equilibrium concentration, those are the equilibrium constant. When I'm dealing with concentrations, I can call it KEQ or KC. And we also had KP. If I'm dealing with partial pressures, then we call it KP to show that hey, this is talking about the equilibrium partial pressures of gases. KSP is called the solubility product constant. So that's the name of it. It's called the solubility product constant. It is the equilibrium constant. So it equals KEQ for saturated solutions. So that's just it. So it gets this special designation. So yes, could you call it KEQ? Yeah, but we tend to call it KSP, solubility product. So it is the equilibrium constant for saturated solutions. So KSP for calcium hydroxide is 6.5 times 10 to the minus 6. If you look in Appendix D, there are some that are like 10 to the minus 22. So even though we would consider calcium hydroxide relatively insoluble, compared to some things, it's a little bit more soluble than others. So the value of KSP is an indicator of, well, how soluble is this? Can I get just the tiniest bit to dissolve, a little bit more? So that value tells you how soluble is this thing. Most of these are not very soluble at all. Okay. So let's look at, we've got a solution of calcium hydroxide. We're going to take some calcium hydroxide, solid, and dissolve it in water. We will get calcium ions in solution, and since this compound has 2 hydroxides for every calcium, we will get 2 hydroxides in solution for every 1 calcium. Let's see, I am going to leave room for an ice table. because we're going to use one on this. When you see the Khan Academy video, they're starting actually finding the molar solubility and then building KSP. So there's different ways to start this problem. Here, our starting point is we're given KSP. We're given the equilibrium constant for this one. Let's write the expression below our ICE table for KSP. So KSP equals, this is a solid, so there will be no denominator in this equilibrium expression. Calcium is to the first power because the coefficient is 1, and then the coefficient of hydroxide is 2. Those two together equals 6.5 times 10 to the minus 6. Oops, ran off the board. It's 6.5 times 10 to the minus 6, what I wrote up there. Now, so what we've done before, we've worked a couple of these before. And so we say, well, I know the value of this. I do not know the equilibrium constants. What is the concentration? I know KSP, but I don't know the amount that dissolves. So I'm going to say minus X. X amount dissolves. When X amount dissolves, I'm going to get, since it's 1 to 1, plus X, concentration of calcium, and then plus 2X, since I have 2 hydroxides per calcium. So these are my concentrations. They're unknown. X amount of calcium and then 2X amount of hydroxide. Now what I want to do is, talk about what is the molar solubility. It is the moles per liter that dissolves. So I'm going to erase this top part so that I can use it. Molar solubility is the number of moles that dissolve per liter. Now that's the same thing as molarity, and molarity is moles per liter, but this is slightly different because I'm talking about the solid. How many moles of this solid will dissolve per liter? So I'm going to leave it as moles per liter. Yes, it's molar here, but let's just, molar solubility is the moles of the solid that will dissolve per liter of solution. So effectively, the molar solubility is this, because we said X amount, X moles dissolve per liter. So this amount is the molar solubility. Trying to work with a small space on the whiteboard, so I'm crowding in a little bit. So that's the molar solubility. It's the number of moles that dissolve per liter of solution. Okay, so we can now solve this. So we've got this. We've got our concentrations, our equilibrium concentrations in terms of X. KSP equals X times 2X squared equals 6.5 times 10 to the minus 6. I can erase this because I have it down. So let's solve for X, and instead of taking video time, I've solved this already, and I got X equals 0.0118 moles per liter. What does that number mean? It says that for this calcium hydroxide, I can get this many 0.0118 moles to dissolve per liter of solution. We can see things, and so from here I would lead you to those 2 Khan Academy videos and section 17.4 on your textbook. So hopefully this gives you a little bit of a lead-in. So that, of course, what can we do with this? And I have some practice. So if I know now, I know KSP, from KSP, I turn it into molar solubility. I can say, okay, what mass would I need to dissolve if I had 100 milliliters? And we can jump off from there, and that's some of the practice. So tomorrow we'll kind of dive into more using the common ion effect and other kind of jumping off with solubility equilibrium.